Now we are going to attempt to find the limit of this difference as x goes to 0 from the right. Now if you recall that the cosecant is the reciprocal of sine and the cotangent is the ratio of sine with cosine with sine in the denominator, then this denominator goes to 0, so this will go to infinity. And here also the denominator goes to 0 and the numerator goes to 1. So this also appears to go to infinity. So let's look at this graphically on what's going on. So say we go ahead and graph cosecant of x, then we can see that as x approaches 0 from the right, cosecant is approaching infinity. And if we look at cotangent of x, that also appears to approach infinity. But if we do this, if we look at cosecant of x minus cotangent of x, okay, that is, this is an infinity minus infinity form. But if you look at the graph of the difference, that is this green graph right here. Let me change the color of that. Let's change it to black. Okay. Still, it is not that prominent, so I can just go ahead and change the y scale to, say, negative 0.5 to, say, positive 0.5. All right, so that way we will see that graph a little more clearly. So now we have cosecant and cotangent disappearing because they were going to go to infinity. But what you have is as x approaches 0 from the right, the difference approaches 0. Okay, and it did look that way when we saw the two graphs. They were very close to each other. But anyways, let's look at that situation analytically. So analytically, if we write this here, then what we have is that cosecant is by definition 1 over sine x, okay, and then cotangent is cosine x over sine x. All right, and then we have, now we have the same common denominator here, and this is very fortunate. Okay, so for those of us who don't like getting into fractions very much. So anyways, so we have this, and now what this becomes is, this is a 0 over 0 form. All right, and you can use L'Hopital or you can use identities further, whichever way you please. Let's use L'Hopital because we know L'Hopital, and what we will do is that differentiate the numerator with respect to x, so that will give us the derivative of x is 0, and that of cosine x is how much? That's negative sine x, sorry, and that of the denominator is cosine x. So what we got now is that we got the limit as x goes to 0 of sine x over cosine x, and what that will be, the numerator is 0 and the denominator is 1, so the limit will be 0 as suggested by the graph. All right, so now let's take another example in which we may have to use some algebraic say ingenuity rather than the L'Hopital, and I'll bring a function that we had in the beginning of the course. Now we are going to look at another example. Here we have to obtain the limit as x goes to infinity of this difference, and you can see the first step goes to infinity, and so does the second one. So this is what? This is an indeterminate form. So what we have to do is we have to find a way to calculate the value. So let's go to Desmos first. So here in Desmos, first we can see that our first term, that appears to go to infinity, and for the second term we had x, and that also appears to go to infinity, and the two are going together very fast. And if I take the difference, so here we go, and then minus x, And that's this green graph, and that seems to be just getting closer and closer to x-axis. We can go ahead and change the value along the x-axis, y-axis. Say we did this, go from 0 to say 1 for the y-axis, and then you can see the situation changes, right? That as x goes to infinity, this green graph is no longer going to 0, rather than it seems to be approaching about 0.5 or 1/2. So let's try to see that analytically or algebraically in this case, because I don't think I can very quickly think of using L'Hopital in any manner in here. So I am doing this, our good old algebra technique, that when we have such an irrational quantity over here, we can go ahead, let me put equal sign here first, we can go ahead and multiply and divide by the conjugate. That's one way. So here is conjugate, so I'm going to multiply by that and I'm going to divide by that, so which would be just like multiplying by 1. Okay, so now here we can use the rule a minus b times a plus b is how much? That is simply a square minus b square. So what that will give us here is a square of the first step, right, minus the square of the second term. Okay, and then when we do that, what we have is that we have here, we will have the square root disappearing here when we take the square, right? And so we simply got that. And now we can cancel the x squares here. And what that will give us simply is this, that we will have x squares cancel, and we got x plus 1 over this quantity right here. And here we can, apply different techniques here. My favorite is, let's just go ahead and pull this x square out. So what will happen is that we can just go ahead and look into this, and you can see that if you are factoring this x square out, all right, let's keep the square root sign intact here, then what will happen? That factors out, so it will walk out from here as simply, that will leave behind an x here, and then an x over x square over here, and then what? And then 1 over x square, right? Okay, and if we cancel this x in this term over here, then what we got is this here. So what we may do now is that we may come down here, and then this limit that we are trying to calculate. Okay, I don't know why I'm trying to rush. You can fast forward me if you would like, all right? Okay, and I'm just going to bring this in here. Excuse me, right here. And what happens here? You can see this here, since x is going to infinity, so we can treat x as a positive quantity. So when we pull it out of a square root, it will become a square root of x square, and which will be x. All right, if it was negative quantity, that will have to become negative x. So what we get now is we get simply this, or we can do it in several different ways. One is this. Let's just split this as a factor of these two. That is, we pulled this out and we factored an x out from here. Okay, and then what happens? You can see this limit goes to 1. You can either go by your pre-calculus rules, polynomial divided by polynomial of same degree, or whichever way, and these two will go to 0. So what we would get, 1 over is square root of, or rather positive square root of 1, that is 1. So 1 over 1 plus 1, which is going to be how much? 1 over 2, as was suggested by Desmos, okay? So, this is a way to determine that this limit here that we were trying to calculate, or rather now we calculated it, that this limit equals how much? This equals 1/2. All right. So let's just go through another example if you have more patience for me. All right. So let's look at another example, and here I just made this function up. I mean, it's not illegal. I just maybe not very interesting or whatever. So I just made it up to show you this example. So here also what you have is this will go to infinity because as x goes to infinity, this input goes to infinity and logarithm will go to infinity. I mean, a little slowly, but still it will. So we have infinity minus infinity form. All right. So we will first go to Desmos and see how does it look in Desmos. And if you want to input a logarithm with base other than e, which you can write as ln, you can just scroll through this function feature. And here it lets you write, let me just put that below here, log with respect to another base, and I forgot the function is 3 to the times 2x plus 5. So here we got 3, okay, and times, okay, 2 to the power x, okay, and what was it? Plus 5, right? Okay, now let me just send it below. So here it seems to go to infinity as x goes to infinity, and the other part was x. So here is a blue graph that also goes to infinity. Now this time these two are not approaching that much together as they did before. And now let's look at the difference that we had. So we got this, and then minus the other quantity x, okay? And now you can see this difference, the green graph, as x goes to infinity, doesn't seem to approach the x-axis. So let's go ahead and determine what this quantity is, okay? So in here, what we can see is that this is the part that gives us exponent, and 2 is the base. So if we can factor 2 to the x out, that may be a way of, and I'm just saying maybe a way of bringing this under little control. So if we do this, if we factor this out, what we will have is, here is going to leave 3 behind as a factor, and here we will have 5 over 2 to the x. And if you do this, log with base 2 of this product, 2 to the x times 3 plus 5 over 2 to the x, then log of a product is how much? Sorry, these are separate. Log of a product is the log of the sum of the factors. So I got this here, and then log with base 2 of the second factor, right? So, and you know this, that log with base 2 of 2 to the x will be x. And then I have plus log with base 2 and then 5 over 2 to the x. All right. So what we just did was that we just wrote this in another format. So let's write that up there and see what it produces for us. Okay. So now we have sorry about that. Okay, we have this here, that is, this quantity is the same as what we did was that this particular quantity can be transformed to, as you see here, x plus log with base 2, okay, of how much? That will be x plus log with base 2, then 3 plus 5 over 3 to the power x, right? Sorry, 2 to the power x, okay? All right, and then what will happen is that we will have these two quantities cancelled, so this becomes simply how much? That simply becomes log of, so that simply becomes this quantity. Now what happens is 5 over 2 to the x will go to 0 as x goes to infinity. So this limit will simply be, I'm just letting the computer do it, but you can see this becomes 0, so that will be log of 3. All right, so that is, it's writing it in terms of, it is log of 3 with base 2, log of 3 with base 2, but what that did was that applied what you call the change of base formula, okay, right here. That is, if we want to change it in terms of, say, logarithm with the same base, I can write it like this, because natural log and common log, they are the frequently used forms of logarithms. All right, so since we did that, let's just do a last example. First of all, we know that our value of this limit is how much? Log of 3 with base 2, or if you use the change of base formula, that will be this quantity. Okay, so now if you are still with me, I'm just doing just one more example of this. That is, here I have got this expression which will be in infinity minus infinity form if we let x go to infinity. So first let's go to Desmos and see what's going on. So we have ln of 3 to the power x, okay, and this one we can just it just recognizes ln, so you can see this is going to infinity, and if we put x in, that goes to infinity as well with a little slower rate. Okay, all right, and if we look at the difference of the two, okay, which let's do that. So minus x, and there's the green graph, and that also appears to be rising. Let's just look at the pattern a little more. Let me just go to 200 here and say 200 here as well. Yes, so that seems to be increasing throughout. So guess will be it goes to infinity, but just let's just go ahead and verify it analytically. So if we come back here, note that right here is our main function, okay, and what we have is the base here, the base is log with base, e here of 3 to the x minus x, and so base here and the base here are different. Okay, so what you may do is this. Remember the change of base formula, that we can change it with respect to base 3, and why we are doing that is this, that will bring this x in the exponent under our control, and this will be log of e with base 3 minus x. So what we get here is log of 3 to the x with base 3 is simply how much? X. So this becomes x over logarithm of e with base 3 minus x, and this can be written as x. And if you did this, took this as common denominator, log of e with base 3, then this will become 1 minus log of e with base 3. Okay, so what we can do now is that we can just go ahead and replace this with this portion right here. Okay, And that is going to give us this here. That is, I just wrote the same expression over here. So as x goes to infinity, this factor goes to infinity. And for this one, this is a constant factor. So let's have the software evaluate that, and you can do that in Desmos. So what you see here is that this is a tiny quantity, but infinity times a positive quantity, no matter how tiny it is, if it is constant, which it is in this case, will be what? Will be infinity again. And if you want that, you can see in Desmos, you can just go ahead and get that value. That is what we want to do is we want to calculate. We have to write that function again. Remember, we can go to calculus and write it from there. Bring it below here. So we got log of log of 3 with base e, and divided by how much? Log of e with base 3. I can just copy and paste it. All right. So what you get is that this is about 0.099. All right, and 0.099 of infinity will again be infinity, as we did right here. So here we saw that infinity minus infinity form can even be infinity. All right.